Hello, in this fourth video in a little mini series which I call Basic Limit Theorems, we're going to look at do examples with the different types of modes of convergence. And we're going to, in the modes of convergence, it's usually one-way implication. So if it converges almost surely, then that implies convergence and probability. But it's not always the reverse, though. Convergence and probability doesn't always imply convergence almost surely. Anyway, so we're going to go through 4 examples here that illustrate that the opposite isn't always true. The first one, we're going to show that convergence and distribution doesn't always mean convergence in the PDF, the density function. So let's, example 1, and we're going to let n go from 1 to infinity, and we're going to define a PDF like this, or a probably mass function, where it's 1/2 if it's slightly less than 1, and 1/2 if it's slightly more than 1, and 0 otherwise. So those 2 points of probability sum to 1. So it is a probability mass function. Now it has a respective cumulative distribution function defined like this, that it's 0 less than this lower piece, and it's 1/2 between the 2 points, and it's 1 if it's greater than that. Okay, so with a picture it kind of looks like this. It's a step function, and then we can see that f and n converges to this distribution. So as n increases, those go down and eventually go away. So it's ultimately this CDF function. It's 0 if it's less than 1, and 1 if it's greater or equal to 1. So this distribution function does converge to a distribution function here. But note that that the density always converges in probability to 0. So it converges to 0, which is not a PDF. So it's not a PDF. And you can kind of think about it like this, that here is the probably mass function, where each of these is 1/2. And if whatever point we pick, say this point here, then as n increases, it's ultimately going to go past that, and it's going to be 0 forever. So for any x that we pick, ultimately this converges to 0. Okay, and so this is a little counter proof that says even though we have convergence and distribution, it doesn't mean the PDFs converge to a PDF. Okay, example 2 it's the classic that convergence probability doesn't imply convergence and almost surely. So let's let xn be a sequence defined on this probability space, where s is the interval from 0 to 1. We're talking about the Borel sigma field on 0 to 1. So this is all types of intervals, way to combine them, intersections, unions. And the probability of measure is the length of an interval. So if we take a sub interval, then the probability of that subinterval is the length. All right, that's how we're going to define the probability. So let's define a random variable on this space, and we're going to do it in a unique way. And that's for each k, we're going to divide the subinterval into that many same length subintervals. So when k is 1, well, we just take the whole interval. When k is 2, we divide it into 2 subintervals. And when the subintervals are like this, and so it just moves across the interval, and then when k is 3, then there's going to be 4 subintervals, and then when k is 5, or 4, there's going to be 8, and for each k we subdivide it more. So now, once we know that about k, we're going to define random variables for each of those subintervals, such that it's an indicator function So we're going to define k 2 to the k minus 1 random variables where the jth random variable in the group is an indicator function for being in that subinterval. Okay, so what the heck did that mean? So let's look at it a picture here. So here is our sample space from 0 to 1. Okay, this is 1/2. And ignore that point S for now. Okay, so when k is 1, we have, it breaks it into one interval, and we're going to let x1 be in this interval. I mean, an indicator for this interval. So it's basically always 1. So then, but now to go to 2, we run out of subintervals, so we have to increment k to 2. So that means break it into 2 intervals, and then we're going to define the next 2 random variables, x2 and x3, as indicator functions over those intervals. So x2 is a 1 if s is in here and 0 otherwise. x3 is a 1 if it's in here 0 otherwise. Then we run out of subintervals, so when x4 comes, we have to increment k to 3, which is 2 to the k minus 1, which is 4. So now we do it into 4 subintervals. So then x4 is the indicator for this piece, x5, x6, x7. So notice that there's 4 subintervals, and if we think of the j as going 1, 2, 3, 4, so the third subinterval is the third random variable of this subset or this group. So then when we get to x8, we run out of subintervals, so we have to increment k to 4, and there's going to be 8 of those. So then it's going to be 8 through 15, you know, x8, x9, x10, and they're going to be indicator functions for these little subintervals. And we just do that over and over and over. And so when we finally run out of an x, you know, a little subinterval, then we have to increment k, and then we drop in the next random variables. Okay, so now let's think about it. Let's let s be this point here. Okay, so then if we go down, it's in this interval, so x1 is 1. Now we go down to this one, it's in this subinterval, so x2 is 1, but x3 is 0, because it's, you know, s is in here, not here. And then we drop down to here. So then x4 is 0, x5 is 1, x6 is 0, x7 is 0. Okay, and so that is like this. Okay, so that's just what I just said. But now for once we get to 8, then we have to subdivide it more. So one random variable in those next 8 will be a 1, and the rest zeros. Then when we run, then we have to divide it again, and then one of those random variables will be a 1 because that s is in that little subinterval. So what that says is that this sequence x1, 2, 3 to infinity never converges, because there's always a 1 that pops up, and so it never converges to differences, you know, to a point less than epsilon. It always goes from 0 and then eventually hit a 1 and then 0, and then eventually a 1, and so it never converges point-wise. Okay, so these are random variables that do not converge almost surely. Okay, so that we've established that fact for now. So now we're going to look at convergence and quadratic mean. Okay, and we're doing that because convergence and quadratic mean implies convergence in probability. So we think that it converges to 0 in quadratic mean. So if we look at this piece, that which is the same as this, and then remember, this is an indicator function, so it's 1 times the probability of that happening, which is the probability of that interval. And so take the difference in the endpoints, we get 1 over 2 to the k minus 1. So now, for n sufficiently large, and remember, as n gets bigger and bigger and bigger, that forces k to get bigger and bigger and bigger and bigger. So for sufficiently large n, we can make this as arbitrarily small as possible, say smaller than epsilon, and that's for any epsilon. Okay, so once we get n big enough that this is the case, then any m that's bigger than n, so we choose epsilon greater than 0, and we choose an m that's bigger than that n that we found over here. So if x n squared is less than or equal to xm squared, which is less than or equal to 1 over 2 to the k minus 1, which then this is less than epsilon, which we established. Okay, so what this says is that since it converges in quadratic mean to 0, that implies that it converges in probability to 0. Okay, that's a fact. We've already established that in one of the earlier videos. So what did we just show? We just showed that convergence in probability does not imply convergence almost surely. It actually also shows that convergence in quadratic mean does not imply convergence almost surely. So example 3, let's define a random variable on the same probability spaces in 2. So this is the interval from 0 to 1. This is the Borel sigma fields. Probability is the interval length. So now for n greater than or equal to 1, let's define this random variable xn, which is equal to the square root of n in this little interval s from 0 to 1 over n. So note that for all s converges to 0. So this is, and it converges almost surely. Okay, so, and what that means is you pick any s in the interval 0 to 1, no matter how small or how big, that if you let n get big enough, this interval is actually going to go below it for any n. So that means at some point in time, xn is going to go to 0 for any s that we pick in our sample space. And that's convergence and almost surely. Okay, that's the definition of it. So now if we look at the quadratic mean, so it converges to 0 almost surely. Let's see if it converges in quadratic mean to 0. So that's this definition, but the expected value squared is, well, this squared times the probability of that event happening, which is the 1 over n, plus 0 times this probability, but that's just 0. Well, this is 1. Well, this doesn't go really small. It doesn't get below epsilon ever. So it doesn't converge in quadratic mean. So what we have just shown, that convergence almost surely does not imply convergence in quadratic mean. So let's look at example 4. So here we have a sample space 1, 2, 3, 4. We're going to let U be the discrete sigma field. So that means all possible intersections, unions, any combination of any way we can combine those. And the probability is going to be the discrete uniform. So that means each one of those is probability happening is 1/4. So it sums to 1. So we're going to define the random variables such that if it's a 1 or a 2, it's a 1. If it's a 3 or 4, it's 0. And this goes on for infinity. And that's a sequence. And let's just define the random variable x to be, if it's a 1 or a 2, it's a 0, which is opposite of this sequence. And if it's a 3 or 4, it's a 1, which again is opposite. So note that the difference between our sequence of random variables and x is always 1. That's the way it's defined. This is true. This is for all s in our sample space. So it does not converge in probability to xn does not converge in probability to x, because we can't make that arbitrarily small. It's always 1. But now if we look at the distribution function of xn, it's this: 0 less than x less than 0, it's 0. It's 1/2 between 0 and 1, and it's 1 if it's greater than 1. Well, the distribution function of x is actually the same thing. It's 0, 1/2, and 1 during these conditions. And so so the distribution function of xn actually equals distribution function of x. So trivially it converges because, well, it equals. So we just showed that even though it converges in distribution, does not imply convergence in probability. Well, that's all I have for this video. I hope you enjoyed it. I sure did. Please like it if you did, and subscribe so you don't miss the next one. Thanks. Bye.